First of all, I would like to thank the organizer team for such a beautiful conference. We have three invited talks today. The first one belongs to Hande Tofali. I will give brief information about Hande Tofali. Hande Tofali is from the Middle East Technical University. Hande Tofali has a background in a solid state physics and works in the field of computational material science. Her group focuses on computational investigation of a broad range of topics ranging from heterogeneous catalysis and nanotribology to polymer composites. And today, Hande Tofali will talk about the single atom catalysis on oxide surfaces, a theoretical investigation. Please, you can start your talk.
Okay, can you see my talk?
Yes.
Okay, perfect. First of all, I would like to express my thanks to the organizers for inviting me to such a diverse and wonderful conference. And I'd like to thank Dr. Kurt for the introduction. So as Dr. Kurt mentioned, today I'll be talking about one of our research lines in our group. So you can see our group members on my slide here. All of these students, postdocs, and researchers contributed to today's results. Today I'll be talking about a very particular kind of heterogeneous catalyst, which we refer to as single atom catalysts. So let me grab a spotlight. All right. In particular, my group works in the theoretical realm of things. We're not experimentalists. I'll be talking about our theoretical investigation on single atom catalysts. So let me go over my outline really briefly. First, I'll define what a single catalyst is and give some background on our theoretical calculations or theoretical investigation rather. And then we will address a few of the issues that are related to these catalysts, namely stability and reactivity. We won't cover the whole spectrum of issues and important points because it's a really large topic. And then I will conclude with a few summary points. Okay, so as I mentioned in the beginning, single atom catalysts are a class of what are called heterogeneous catalysts. A heterogeneous catalyst, as opposed to a homogeneous catalyst, is one where the catalyst is in a different phase than the reactants. So let's say we want to oxidize carbon monoxide. So carbon monoxide and carbon dioxide, which is the resultant of this reaction, and also the oxygen that oxidizes carbon monoxide, are all in the gas phase. However, the catalyst, in the case of heterogeneous catalysis, is usually a surface or a metal cluster. And you can see one example on the picture here on my slide. So here on this slide, we see an example of ruthenium and iridium nanoclusters on zinc oxide. And as you see, these nanoclusters, especially the metallic component, tends to be rather small at the nanometer scale. There's a reason for that. And this is an example of a heterogeneous catalyst. So heterogeneous catalysts have usually higher stability than homogeneous catalysts. They're easy to separate. So the catalyst itself is in the solid state, so it is easier to separate than the homogeneous catalysts from the reactants or the resultant products. Also, since metal dispersion can be very well controlled and the metal components can be rather spread out, it lowers metal usage. However, some clustering of metals is usually unavoidable. So the objective here is to lower the metal component as much as possible. So at the limit of this procedure, where we lower the heterogeneous catalyst, is the single atom catalyst. But before that, let's see the components of a heterogeneous catalyst. Usually we have a support. This is necessary to, first and foremost, provide a structure to the system to hold the metal component and also the reactants. But this is not the only function of the support. It may also, depending on its interaction with the metal component and the reactants, it may also modify the properties of the reaction itself. So here you see an example of what I believe is alumina and a nickel cluster, some different sizes of a nickel cluster. So as you can see, the system offers many absorption sites, both on the metal cluster, but also at the interface of the metal and the support. And all of these are interesting sites to investigate because they all have different chemical properties. So the supports that we are going to look into today are oxides. Oxides are preferable because they usually offer an open surface, and defects can be easily introduced into the system. The metal component, on the other hand, is usually some sort of metal with partially filled d orbitals. And as I said, the smaller the cluster, the better, because we are shooting for a higher surface to volume ratio. Now, at the limit of the surface to volume ratio, as it tends to zero, is the single atom catalyst. So, if we manage somehow to put one metal on the surface, this affords us maximum. This should, in theory, afford us the maximum reactivity because it maximizes the unsaturated bonds. Excuse me. Here in this picture, you see one such example. This is an example from our own studies. Here is a magnesium oxide surface. Here is our metal component. In this particular case, it's iridium. And here are our reactants, the oxygen molecule and carbon monoxide. This is the literal reaction that I mentioned in the beginning. We are looking at oxidation of carbon monoxide. So, single atom catalysts are thought of as being best of both worlds of homogeneous and heterogeneous catalysts. And the mechanism behind these systems are usually as follows. The d orbital of the metal forms a bonding orbital with the bonding orbital of carbon monoxide. Also, the d orbitals, the remaining d orbitals of the metal can also pair with the anti-bonding orbitals of carbon monoxide to form the anti-bonding orbital of the full complex. Now, the objective here, in order to make use of the reactivity of the metal, the idea is to depopulate the bonding orbital and populate the anti-bonding orbital. So this is how. Of course, the real picture is much more complicated than this, but this provides an intuitive model regarding how the reactivity of the metal works. So the idea is to weaken the carbon monoxide bond. In our case, of course, this can be many other reactions, but in our case, to weaken the carbon monoxide bond in order to eventually break it. Wonderful as they are, single atom catalysts offer also many challenges. The biggest of these challenges is stability. So at this point, fabrication methods are very well optimized. These can be done in myriad ways. Some examples are modification of precursor complexes. So you have a metal-centered big complex with some ligands, and then you try to get rid of the ligands once the complex is adsorbed on the surface. Or you can use regular dosing methods, but just really lower the metal component and hope that you get single atom catalysts. And there are also many other wet chemistry methods, so on and so forth. Now, in this picture, you see an iron oxide surface with the individual, this I find really quite amazing, the individual iridium atoms on top. This is an experimental picture, of course. Speaking of characterization, there are also many well-developed ways of characterization, including X-ray adsorption, imaging techniques, vibrational techniques such as IR. But as I mentioned, the biggest problem is the stability. So metal atoms are quite mobile on surfaces. So what happens is that once they get free, once they break free of their adsorption site, they tend to diffuse very easily and cluster together, find one another, cluster together, and lose their reactivity. So it defeats the purpose of having a single atom catalyst. So the trick is to find a support that, while keeping the reactivity of the single atom, also binds it quite strongly and keeps it in place. Okay, so after this introduction, let me give you another brief introduction on the theoretical side of things. As I said, we're not experimentalists. We look at these problems using modeling. So in our work, we particularly concentrate on two metal atoms, iridium and rhodium, on three oxides. In fact, we work on five oxides. We work also on titania and lanthanum oxide. However, today, due to time constraints, I will be presenting results from just three oxides, namely magnesium oxide, zinc oxide, and alumina. Now, as I said, there's stability. There's the big problem of stability and associated side problems. And I will try to sort of give examples of how we address each of these problems using theoretical calculations. So as I said, the biggest problem is stability. It's very important to stabilize the metal atom on the oxide surface. How does one do that? You try to optimize the support and the metal simultaneously to find which metals bind strongly on which oxide surfaces. So we're looking at large adsorption energies. Also, we are looking at high diffusion barriers. If the metal manages to break free from the surface, it shouldn't diffuse quite so quickly. If it manages to diffuse, also an important parameter is how easy it is for metals to come together and form clusters. So the smallest cluster one can think of, other than the single atom, is the diatomic cluster. So we also look at formation energies of diatomic clusters. Detection, so vibration frequencies can be measured and calculated quite accurately. So we also look into some ways of giving some ideas to experimental partners regarding which adsorption sites of our reactant molecules provide which frequency, so that once they measure frequencies, they can have an idea, comparing with our results, they can have an idea of which adsorption sites are viable to our reactants. I won't be presenting results from vibration frequencies because of time constraints, as I said, but we are able to calculate them. Also, of course, reactivity, how reactive are the metal atoms? So theoretically, they should be very, very reactive, but is it really true? Are they as reactive as predicted, or are all combinations of support and metal atom give reactive catalysts? In order to study reactivity, we look at two parameters, carbon monoxide adsorption energies. Carbon monoxide is a common probe molecule that is often used in such calculations. And also, again, a probe reaction, which is an important reaction in and of itself, but also a simple reaction for us to study in brief amounts of time. In particular, we are looking at carbon monoxide reacting with an oxygen molecule, forming a carbon dioxide molecule and an oxygen molecule. So the reactants, carbon monoxide and oxygen, can be in the gas phase or can be already adsorbed on the surface. The reactant, carbon monoxide, carbon dioxide, sorry, the product, carbon dioxide, is usually in the gas phase, and the remaining oxygen atom is usually left on the surface. Now, this isn't the only reaction path that this reaction can happen in, but this is the one we look at. Okay, so just to give two slides of information about the theoretical background of our calculations, we use the famous density functional theory, which is going to be at least somewhat familiar to most of the audience. Density functional theory is a quite simple yet ingenious way of handling quantum mechanics. So in quantum mechanics, we assume that once we solve this complicated differential equation, where the first operator describes kinetic energy and the second operator describes any interactions in the system. Once we solve this incredibly complicated differential equation, we know everything there is to know about both the ground state and the excited states of your system. Once you know your energy states and the energies that correspond to those energy states, the assumption is that you know everything about the system. Unfortunately, this proves quite impossible. These are very, very complex equations, and closed form solutions are not available beyond the most simple of the systems. However, over the past several decades, many approximations have been developed. Some approximations concentrate on the wave function to find approximations to the wave function. Some others tend to reformulate, model, or shift the focus from the wave function. Density functional theory is one such example. So instead of concentrating on the wave function, we shift our focus to the electron density. So the electron density is a measurable, observable. However, of course, it's not the wave function. It doesn't give everything about the system, but it gives a lot of important information. We write the density in terms of single particle-like orbitals. The details are not that important. These orbitals are in the beginning not specified. We have to solve some equations to get to them, but we can write the density, ground state density, using these orbitals. Now, using these orbitals, we fashion some sort of kinetic energy. This is, of course, not the true kinetic energy of the system, but a pretty decent approximation. Then we write down the external energy, which in our case is the interaction with the nuclei of the electrons, and the electrostatic energy. So none of these terms at the moment involve any kind of correlation or interaction between the electrons. In particular, it does not allow for antisymmetry. All of those quantum mechanical effects are hidden away in this term, which we call the exchange correlation energy. Now, this is very affordable. You don't have to solve a very complicated equation. You solve an only slightly complicated equation. However, your approximation is only as good as the approximation you make to this exchange correlation term over here. Okay, so this is all I will mention about the background. So what can we calculate? Of course, if you sacrifice the wave function, you sacrifice a lot from what you can know. And of course, this results in DFT being only a ground state framework. So the only reliable quantities, we extend this a little bit, but really the sort of the real reliable quantities are total energy differences at the ground state of systems, forces, equilibrium geometries, density related properties, and anything that you can derive from these properties. So of course, metal adsorption energy is a very good candidate because it only relies on ground state energies of the components. So you calculate the total ground state energy. From that, you subtract the energy of your substrate and the energy of the isolated adsorbate. So metal adsorption energy, which is important for stability, can be calculated quite reliably. Okay. Related to reactivity, as you remember, I mentioned that we need to shift occupation from one orbital to another. This also reflects in charge redistribution. So you can calculate charge redistribution upon adsorption. Similarly, reaction barriers, we need to employ an extension to DFT, which is called nudged elastic bands, but this is pretty well developed. Also, partial charges. So how much charge does your adsorbate acquire upon adsorption to your metal system? Finally, vibration frequencies can also be calculated very easily, not easily, but quite reliably. It's only a matter of writing down the dynamical matrix and solving for its eigenvalues. I'm not going to present any results today on the vibration frequencies. Okay, so one more thing that I should mention before I go on to our results is, of course, adsorption energy of the reactants is also an important descriptor. The adsorption energy of your reactants, as you can see in this plot here, correlates the activation barriers of your reactions correlate with the adsorption energies of your reactants and also the charges on your reactants. So this is also quite important. Okay, so let me show a few examples in the remaining time. Let me show a few examples from our work on this topic. I'll address stability and reactivity and leave aside all the other points that we address. So let's first start with metal adsorption energies. Because stability is very important, it is imperative that we stabilize our single metal atoms. One very often used surface for this is the gamma alumina surface. The gamma alumina surface, as you can see in these pictures, is an open surface which affords many different adsorption sites. So these are the high symmetry points. Some look similar, but it depends also on what's underneath. So G and H look similar, but they are not because of what is under the surface. So we took our metal atoms and absorbed them on all of these sides. Then we run them through a geometry optimization, and see their absorption energy. So just to provide a metric, absorption energies that are higher than about half an EV are considered quite good. Absorptions higher than 1 EV are considered really good, really stable. Uh, So upon geometry optimization, we got these energies. So here in this table, you are seeing the absorption energies of iridium and the charge that accumulates on iridium. Also, as a side note, the magnetic character of the iridium atom designated by its magnetic moment. So let's keep in mind the highest energies. As you can see on site A and G, we get the largest energies. They are quite similar. So they are almost 3 eV, especially A. So we have an absorption energy of almost 3 eV. All the rest are still quite high, but much lower than these two. For rhodium, also, we get a little bit higher than 2 eV, close to 2 eV, similar magnetic moments, a little bit low charge accumulation. From this, the conclusion we get is, of course, the under-coordinated surface atoms here in this large crater that you see on the surface. So it's like an open hole, basically, on the surface, of course, affords many strong adsorption sites. We find that iridium, although iridium and rhodium usually behave in a similar way, we found that iridium is quite a bit more stable than rhodium. And there is a sizable charge transfer accompanying these strong adsorptions, as in a way expected. And this is a good thing because charge transfer is an indicator of reactivity, also, as we saw in the previous slides. Also, one more indicator of reactivity is the magnetic moment. Magnetic moment arises from unpaired electrons. So if you have an unpaired electron, it means that you are likely to form bonds. Okay, but the question is, okay, great. Alumina, as expected, in a sense, provides a really strong sort of anchor for the metal atoms to hold on to. But if the metal atom breaks free, are they mobile? Can they diffuse easily? So for this, we considered a very large number of diffusion paths and used Nigel elastic bands to calculate the diffusion activation barriers over these. Some of them did not result in good results, so we excluded them from our results here. But the more important ones gave us these activation barriers. So as you can see, for iridium, path number 3 gives an activation barrier of almost 3 eV. So this is a really huge number. Not only are the atoms really strongly bonded to this surface, but also it is difficult for them to diffuse. Of course, some other paths provide easier diffusion, but that's expected. The conclusion, however, is that this is a very stable surface for absorption of iridium and rhodium. So how about a less open surface? Next, we consider the same problem, but with magnesium oxide surface. This is a very sort of regular, close-packed kind of surface. And of course, it's very symmetric, so it doesn't afford that many different paths of diffusion for the atoms. So we looked at over the bond, oxygen to oxygen, and hollow side to hollow side diffusion over the oxygen. And as you can see, this is our reaction coordinate along the reaction path. And the maximum energy here corresponds to our activation barrier. So as you can see, we got diffusion barriers that are much smaller than aluminum, but still not too bad. So we get sort of these 0.2 EVs, which provide very easy ways of escaping. But also we get these larger diffusion barrier energies as well. So of course, magnesium oxide is not as good a trap for metal atoms as aluminum. Okay, so we covered absorption, we covered diffusion. How about formation of clusters? So if these atoms find one another, are they likely to form clusters? For this, we looked at the magnesium oxide surface, and we calculated the absorption energy of the second metal atom to the first metal atom. And of course, as you can see, the absorption energies are huge. I mean, these.
Sorry, dear Hande, you have 5 minutes to finish.
Sure, sure. I am watching the
Okay,
time. Thank you.
okay,
Thank you. I'll be done in time.
okay.
So as you can see, these metal atoms, when they find one another, they really, really want to bind. So you really want to keep them in place. Okay, so let's now talk a little bit about reactivity. We talked about stability. So first we look at carbon monoxide adsorption. Remember, adsorption energies are important descriptors. We first look at the adsorption of carbon monoxide and alumina, just to get an idea of how much it would absorb without, how strongly it would bind without the metal component. So as you can see, carbon monoxide is at best very weakly bonded, at worst unstable on the surface. So this positive absorption energy points to instability. However, it's a whole different story when we bind it together with a metal atom. The interesting thing is that it binds strongly even when it is far away from the metal. So the metal is here, the carbon monoxide is here, or in this case, the metal is here, carbon monoxide is here. So even with that, you see a sizable improvement on the absorption energy. So not only is the metal providing a reactive site, it is also modifying the absorption on the other parts of the surface. So this is an important finding. Of course, if you absorb the metal directly on the metal, then of course the absorption energy is really, really huge. So this has a very important stabilizing effect on the adsorbate. So once the metal is stable, it stabilizes also the adsorbate. So as you can see, this is a lot of information, but the important point is to notice these large absorption energies. These large absorption energies are also accompanied by large charge transfer onto carbon monoxide or out of carbon monoxide. This is another indication of reactivity. Also, in addition to finding large absorption sites, we look at different surfaces. So as you can see, if we look at two different surfaces of magnesium, the magnesium 110 surface is a much stronger anchor than the magnesium 001 surface because, of course, it has these ridges which provide under-coordinated atoms. Similarly, if I look at carbon monoxide absorption, 110 surface with the iridium atom provides a much better absorption or absorption support than the 001 surface. Finally, the final thing I wanted to show before my time is up is defects. So here we have a zinc oxide surface. Instead of using the perfect surface, in this case, we used a defective surface. So we took out one zinc. Instead of the zinc, we put in an iridium. And as you can see, second metal absorption did not get worse. So it's still a large energy, but it's not worse. And as you can see, the bond here between this bonding orbital that you can see on oxygen is now depopulated. So it works as we expect. And in fact, when we used this defective system to study the oxidation, the activation barrier was found to be 0.6 eV. This is quite low, so it's a really good catalyst. And the reaction energy was found to be 2.3. So this reaction on this surface is incredibly exothermic, so very likely to happen at low temperatures with a very, very low activation barrier. So this defective system works really well as a catalyst. Okay, so here are my conclusions. I will not go through them. I already talked about them, but I just wanted to acknowledge our funding agency, which is TÜBİTAK, with this grant number within our calculations on our national clusters, UHEM and TRUBA. So I'd like to extend my thanks to the audience and the organizers once again, and I'd like to take any questions if there are any.
Dear Hande, thank you for your beautiful presentation. You gave everything in detail
Okay,
about
great.
the zinc oxide. This is very important, especially for infrared detector. So, do you have any questions, dear participants, for Hande Tofeli? Please let me know.
Yes, one question.
Yes, please.
Do you interest hydrogen included molecules for the absorption for these surfaces?
You can, we not in this case, we only, our focus is not so much the reaction itself, but the surface. So we didn't look into that, but we can. I mean, we've done alcohols in the past. You can study any reaction you want, but we are just concentrating on carbon monoxide oxidation at the moment. But thank you.
Thanks.
You're welcome.
Are there any questions for Hande? I think there is no questions, Hande.
Okay.
Thank you again for your contribution.
Thank you very much.
Conference. We will glad to see you again at different conference. So, thank you. We okay. Do you hear me? Okay. The second talk belongs to Keisuke Takahashi. He is from Hokkaido University from Japan. I will give short biography. Keisuke Takahashi is associated professor at the Department of Chemistry at Hokkaido University in Japan. He is also the principal investigator for the Catalysis Informatics project as funded by GSP CREST, where he conducts research in materials and catalysis informatics. Okay, we can start here.
Okay, can you hear me?
You are welcome. You are welcome. Thank you for participating.
Okay, thank you.
In this conference.
All right.
Okay.
Okay, so can you guys hear my voice?
Yes, I can hear very well your voice.
Okay, great. Okay, thank you for inviting me. So I'm an associate professor at Hokkaido University, Japan, and today I'm going to talk about how to design the catalysis using data science and machine learning. And so my talk is a little bit different from some of the guest talk here. So the idea we are trying to do is, trying to design the catalyst from data. So yeah, let me switch to the pointer here. So here, as you can see, if you look at the history of the catalyst or science in general, this is how you can see it here. So up to 1950s, people has been doing experiment and theory. And 1980s, the computational science came out, which is, the density function theory took a major role here. And since then, as you guys see, that most of people do DFT work, and it's quite a powerful tool to understand the mechanism of the materials. But around 2010, the new science came up into the material science and the catalyst science, which it's called data science. And this was originally started in 2008. The United States actually started a project called Material Genome Project, as well as the Catalyst Genome Project. So what they're trying to do is they're trying to create or design the materials from material data. So the idea is, okay, maybe we can design the material from data science or even artificial intelligence. So this is a field I'm actually working past 5 years. And today I'm going to talk about how can I design the material from the data. So that's what I'm going to talk today. So the first thing is it's actually called materials informatics or even data science. And a lot of people still don't know what this is. So I'm gonna actually briefly explain what is informatics is and what is machine learning is before I talk more detailed. So the word informatics is actually the idea that basically you apply the data science to design or solve the problem using the data. So the idea is quite simple. If you have a data, and from data, you actually use data science to design something. And so to do that, you need actually 3 steps to do it. The first thing you have to do is you have to have a data. So you need a material database. So once you get the data, then you have have to actually create the, basically design something from data. So how can I get the knowledge from data? So here people actually use data science technique here, which is, it can be machine learning, artificial intelligence, scientific visualization, statistics analysis. It can be in any type of data analysis is involved here. So today I mainly talk about those parts here. And then also, if you want to actually manage data science, database, data science, and many other techniques, you also need a platform to organize everything, how to share the data, how to people can use data science without any hard programming language or anything. So basically, you need those database, data to knowledge, and also the platform. And I'm going to actually talk about what I have done today, in the past few years. And so today I'm going to introduce the field called catalyst informatics, and basically, try to combine catalyst science and informatics science. And this time I'm using oxidative coupling method as a target reaction. So the reaction is quite simple. As you can see, you basically crush the CH4 and the O2, and then try to get C2H4, which is ethylene, and then try to get the water with it. But this reaction is quite complicated because, a lot of byproduct is CO or CO2. So it has been kind of a challenging field. But what I'm trying to do is, okay, we could possibly design the catalyst from the data. That's what I'm going to present today. And this is actually my groups in Japan, and I'm actually managing a pretty big group in Japan. So our group is aiming to design the catalyst from data. So to do that, we actually create own database using high throughput calculation as well as high throughput experiment. And then from there, using data, we actually apply data science technique, which is machine learning and also the data mining. And then from here, we actually predict the catalyst, and then we confirm if those catalysts works in the experiment. So as you can see, we create the data and then we predict catalysts, and also we validate in the experiment. So that's the workflow, basically the group we are doing it. So today we're gonna introduce what we do in my group. So first thing we have done is we're working on the oxidative coupling method, and we try to predict the catalyst from literature data. So basically, I'm collecting the data from academic articles as well as patent. So if you look at the past 30 years of basically article in this field, we are able to find roughly 1,800 oxidative coupling method catalyst data. And whenever I visualize this data, this is what you can see. So this is a CH4 conversion. So how much CH4 was converted. And then y-axis, we have C2 selectivity. So within the converged CH4, how much we got the C2, which is ethylene and ethane was actually acquired. So if you plot it, as you can see, if you convert more CH4, you don't get so much C2. But if you convert less CH4, then you get more C2 selectivity. So as you can see, this has the inverse proportional data is actually C. So, but in reality, what we want to get is we want to convert more CH4 and then we want to get more C2. So this is the target area we want to do it. And past 30 years, people couldn't achieve this area. So what we are trying to do is, okay, from this data, can we design the catalyst? That's what we did first. So within this data, I'm going to skip the detail of how we did machine learning and stuff, but what we did is we implemented machine learning, which is, it's kind of like a type of the artificial intelligence. So machine is going to learn this data, and then based on this data, machine is going to design something for us. So that's what we did. So by doing this, machine actually proposed two type of important feature here. The first thing is the machine told us that if you want to design the catalyst, of course, you need to get basically the composition name, like what kind of element is important. Those kind of catalyst information is important. But also, machine actually told me that the process information is also important. So even you actually find a good catalyst, you also need a good experimental condition. So, what kind of temperature, what kind of pressure, what kind of, CH4 flow is important. So basically, you have to get both. You have to optimize catalyst as well as experimental condition. So that's what machine told us. So we just cannot only look for the catalyst. You also have to look for the processing condition. And also, machine told us roughly 20 catalysts was actually found here. And some of the catalysts is not even discovered before. So what we did is, okay, let's test this in the experiment. That's what we did. And we tested in the experiment, and this is a result we actually got. So this is the transparency data point is literature data. And this is red star is actually a predicted catalyst, and then we did it in experiment. So as you can see, we couldn't actually reach this target area. But what we notice is we can actually do the interpolation fitting, which is within the data, we can actually get some good high point here. So some of the catalyst is quite high active, so we are able to find a good catalyst. However, as it's saying here that we couldn't predict anything higher here. So we did a little bit more analysis why we couldn't predict a good catalyst here. And then we did some more analysis, and then we discovered that this is how machine predicted. So this is the like a true seed yield, which is in the experimental literature data. And this is the one machine predicted. And then some of the data machine couldn't actually predict it. And then we did more analysis, and then we actually find out that C2 yield more than 30%, like those high C2 yield catalysts, they are actually quite different from best of the data. Those are actually patent data, or more like let's say they didn't focus on the catalyst, more like they fix what they tune the experimental condition. So basically the trend in the data was quite different, and that's why we couldn't actually predict it. That's what we find out. So from here, we actually find out that literature data from past 30 years of article can be a little bit tricky, because basically whenever people find a new catalyst, they actually tend to focus on one specific catalyst. So data can be quite biased. Even people find a new good one, people only focus on those something similar catalysts. And also some of the data, some of the data is not quite consistent. Like some patent data is they tune or fix the experimental condition. So it's not quite representing catalytic properties. So literature data can be quite challenging as well. It's biased. So we realized that, okay, we have to create data ourselves. So we actually developed the devices. It's called high throughput experimental devices. And this is how machine looks like. And this one, we actually mix the CH4 and O2 gas, and then we actually implemented 20 catalysts at the same time. So within one day, we can carry out roughly 1,000 experiments can be done. So normally, as you can see, past 30 years, so only like 2,000 catalysts was tested, but just only one day we are able to present like 1,000 experiments here. So total, we are able to get 60,000 experiments we carry out in just 3 months. And from there, as you can see, CH4 conversion and C2 selectivity data point was clearly see the inverse proportional map here. And then from this data, okay, we are like, let's design the new catalyst. That's what we are trying to do here now. So within the machine learning, we couldn't quite predict data from literature data. As you can see, this is a predicted C2, and then this is basically machine predicted, and then this is a true C2 selectivity. As you can see, we are not able to get the correct line. Normally it should be 45-degree of line here. So we couldn't get anything correctly. But with our high throughput data, we are actually able to predict clearly. So the difference is the data in literature data is not so consistent. People think literature data is great, but in reality, the data is quite biased, and some of the data is not trusted. But if you actually get data on same people, same experimental equipment, and around the same time, you can actually get a good trend. So I think we realize that it's quite important to collect own data. So if you can create own data, it's quite easy to predict. That's what we find out. And from those big data, we are actually machine or artificial intelligence can easily predict experimental condition and catalysts. So as you can see here, machine can actually, we pick certain catalysts here, but machine can predict what would happen if you change the temperature and if you change the CH4 flow and O2 flow, and how much C2 it actually can get. So as you can see, machine can easily predict experimental space easily. You can clearly see maybe temperature is 800 and CH4 is maybe 3 is good. So those kind of things, normally you have to do one by one in experiment, but machine can pretty much give you the whole answer here. So you can roughly design the experiment here. And then later on, we also tested the experiment. And as you can see, this red dot is what experiment we did experimental confirmation. So basically, machine predict is basically supported by experimental confirmation here. And also, we are able to predict new catalysts. And we discovered that at 800 Celsius, like if you put like manganese, titanium, nickel, as well as some heavy element, if you put those catalysts, you can get high C2 yield. We can also predict something like that. And with this one, we are able to achieve like 28% of catalyst before catalyst. So machine learning is basically quite powerful. With such a short time, you can actually predict catalysts, but also you can actually represent experimental spaces very easily. So this is going to pretty much change how we can design the catalyst. And then next thing we have done is we actually implemented deep learning, which is some of you guys might have heard about deep learning. This is basically one of the most sophisticated artificial intelligence. So within this catalyst big data, we actually implemented deep learning and see if we can design the catalyst. So that's what we have done. So with deep learning actually predicted 20 catalysts that's supposed to have quite a high C2 yield. And as you can see here, the machine learning predict this 20 catalysts has quite high yield, which is this black bar here. And then we tested in experiment, like those catalysts are really good catalysts or not. And as you can see, two catalysts here, this two catalysts here has quite a high C2 yield. And we confirmed the experiment, which is those two catalysts. And those two catalysts has quite a high C2 yield, which is 18% each. And those composition of catalysts has not been reported before. Like this was completely new catalyst. And in this OCM catalyst, like having 18% to 20% is actually really good catalyst. It's always really hard to find those type of high active catalysts. But with machine deep learning, we are able to find those two active catalysts just in like very short time, like 1 month of research. And normally it takes like 3 to 4 years of research to get this type of catalyst. So what we actually can say is that deep learning can really design the catalyst, and it's much faster than what we normally, human researcher can do it. And we also compare how much deep learning is better than random choice. Random choice is like, random choice by human. So we did some, basically the testing here. So as you can see, let's say human picked 59 catalysts and then deep learning picked 20 catalysts. And C2 yield about 10%. Random choice by human can get 10% of C2 is like 57% of chance. So it's 34 out of 59, it got 10%. But deep learning, 18 catalysts out of 20 catalysts was actually over 10% of activity. So as you can see, it's much higher probability to get better catalysts than what human do. So what we can say is deep learning is probably much smarter and better to design the catalyst than human. So that's what we actually discovered here. So so far what I have actually shown here is, in the future, we have been only dealing with, experiment or theory to design the catalyst, but I think data science can be potentially be another choice to design the catalyst. So I think the whole research is probably going this way in the future. So this is what I actually talk here, and I only have probably 5, 6, 7 minutes. So next thing is I'm gonna actually talk about platform that my group is developing, and then I will finish my talk today. So platform is basically this is a place you can share the data, you can do analysis, and so anyone can upload your own data and then do some data science analysis. So our group actually developed the platform called Catalyst Informatics platform. It's called CATS, and it's already available and it's already published as a paper. And this is actually quite probably it's free to use and anyone can use it. So I think if you have own data, it might actually helpful to use this type of platform. And this work, what you can do is you can do multiple things here. And then I'm gonna quickly introduce what we can do here. So you can basically share your data and upload, or you your data. And of course, you can make it private if you don't want to share with them, and it's free to use. So as well, basically, right now they have like 7 data set provided by our group as well as some other group is already there. So if you want to do some analysis, data is already there. Of course, you can upload your own data. But if you click data here, you get to see the whole, where the difference data is coming from, and then you can actually see the data sheet, just like what you see in the Excel. So we are hoping that this will act as catalyst data center. So people in the world can upload their own data, and then your data can be reused in the future. That will be probably the best in this field. And then also you can do some visualization analysis here. So if you select some data in your data, or it's already uploaded data, you can create scatter plot as well as some Excel file here. And what's powerful about this thing is you can actually plot some scatter plot, and then you select the data here. So you can highlight what's the data here. Then immediately this highlighted area is going to be highlighted in the Excel sheet. So you can easily see what data you are looking at. Sorry, it's actually written in Japanese. But basically what you select is automatically reflects to the data sheet. So you can actually create multiple different type of graph, and then they're all linked to each other. So you can see that some of the outlier can be easily detected, or you can do some sort of analysis. You want to look at the specific area, and then you can see the real value here. So those can be easily done here. And also, we made machine learning much easier to use. And normally, it requires some heavy programming, but here you can just do everything by click, and basically, you can do basically clicking here. So if you have a web browser, you just open this page, and then you just pick what kind of machine learning or artificial intelligence you want to use, and then what kind of descriptor, which is the data you want them to study, and then what you want to actually you want to actually predict, which is target variable here. So you just click everything and you select it. And then if you submit, they automatically create a machine for you. So machine learning can be just done by click, and then it's just mouse and click. And then after you create a machine, you can also predict what would happen. So if you just put the experimental condition and catalyst data, machine is going to predict what would happen. And those things can be all done in web browser. So that's how we try to make everything easy, so that more people can work on the catalyst informatics. So I'm going to actually summarize today's talk. As you can see, catalyst informatics is quite a new field, and I only kind of focus on the machine learning, but this actually field consists of multiple different fields. The machine learning, of course, you can design, but high throughput experiment or high throughput DFT can basically collect the data, and also data mining to get the new knowledge, and then also scientific visualization, and then also platform so that many users can use it. And then of course, you can also get the information from measurement. So if you analyze XPS or ZAFS or many other techniques to get basically the characterization technique, you can also use those data to use informatics. So what I actually want to say is this is quite a new field, and it just started and got popular past 2-3 years. And I'm one of the few people working on this field. But I'm hoping that this type of field is going to be more popular, and then it's going to be an alternative way to design the catalyst. So, and then last thing I want to say is basically my group is really open to research collaboration. And basically I got invited because I'm also working with one of the Turkish associate professor who is actually just joined the Zoom meeting today. But I'm quite happy to work with Turkish people a lot. And we are also looking open for the research collaboration. And then also my group is always looking for the PhD student postdoc. So if you're anybody interested, please contact me. And thank you for listening today. And that's it for my talk.
Thank you, dear Keisuke Takase, for your detailed conference. And I would like to say add something. We have historical ties with Japanese people from Asia. You know that Turkish and Japanese were neighbors in Asia. So we are glad to see you host in our conference, and we would like to see you at another conference. And I hope that Japan and Turkey will increase their cooperations in cultural, in social, in science, and technology. You are welcome every time for Turkey. And
thank you.
Dear Keisuke Takashi, we have one question from Hande Tofoli. Her question is like that. Which descriptor do you use for the learning model? Which descriptors do you use for the learning model? This is a question for you.
Okay. For this type of catalyst work, we actually, it's written here, so I should make it more clearly. But we actually use a catalyst like element information. So element, basically catalyst composition, and then pressure of the CH4 and then O2, and then also the temperature. That's the descriptor we have used. So hope this helps or answer your question.
Is there any questions for Takashi? I think there is no question. I will again thank you for your participation in this conference. Thank you. Thank you.
Okay, thank you.
You are every time welcome to Turkey.
Yeah, I think our culture is really similar.
After the virus is over, we would like to see you in other conferences face to face. So
yeah, that would be better. Yeah.
For your contributions.
Thank you.
Thank you. Thank you again. Thank you. See you. The third invited talk belongs to Itsuki Miyazato. Itsuki Miyazato is from Hokkaido University from Japan. And I will give short biography about Itsuki Miyazato. Itsuki Miyazato is assistant professor at Department of Chemistry at Hokkaido University in Japan. His research interests are focused on the integration of both theoretical and experimental material data via data science in order to design novel materials. His talk is about turning electronic properties of two-dimensional materials by doping the transitions metal. Yes, welcome. It's the
Can you hear me and see my slides? Okay, okay.
Yes, yes, you can
my
hear
presentation. Okay,
yes,
hi. Okay, thanks. Hi, I'm Itsuki Miyazato from the Hokkaido University in Japan. Actually, I'm joining the CREST Catalyst Informatics project with Associate Professor Keisuke Takahashi, who is the previous presenter. And today, I would like to give a presentation entitled Tuning Electric Properties of Two-Dimensional Materials by Doping the Transition Metal, which is a different topic to Catalyst Informatics. But I hope you can enjoy my presentation.
Yes, we can progress.
From the discovery of graphene, two-dimensional materials have been popular in material science because of the unique physical property originated from its high surface area and the quantum size effect, which is rarely seen in conventional and bulk materials. Because of that, many types of two-dimensional materials have been explored via both theoretical and experimental approach. One of the most unique property of two-dimensional materials is electric property. Two-dimensional materials usually have complete different physical properties compared with the bulk materials. Here's the example of the MOS2 in electric structure. Bulk form of MOS2 have an indirect band gap, although its monolayer have direct band gap, which is the important factor to design electric devices. That is one of the reasons of the popularity of two-dimensional materials in material science field. And as you can see, two-dimensional materials can be tuned its property by structural manipulation, such as doping, inducing defects, and adding strain, interaction, interfacial interaction, and ion interaction, some kind of thing. By doing this, this shift of the change of properties by those manipulation, it's not explored systematically yet, which is the key to design a new application for the two-dimensional materials. Additionally, data science can accelerate to predict novel materials, which the Professor Takahashi said, and by capturing the trend of the accumulated data. So I would like to present the example of the tuning electric properties of the two-dimensional materials via structural manipulation and data science technique. Here, firstly, I would like to introduce our research on zircon doping effect on trichalcogenides, HFSC and HFSC3. And this research result was reported on the following research article with a collaboration with the following researchers. I think two researchers from Turkey. In this research, systematic zircon doping into the HFS3 and the HFSC monolayer performed and investigated their shift of electronic properties. I think some people here knows that the HFS3 and the HFS3 is known as a two-dimensional structure called transition metal trichalcogenides, which is abbreviated as TMTCs. And the typical TMTCs, the structure of typical TCs shown as those images. By evaluating property changes, 9 different zircon concentration, I mean, from this formula in this 9 concentration, I mean, in the HFS and the HFC are considered. All evaluations are performed by a first principle calculation. Here are all considered structure of doped HFSC and HFSC monolayer. Doping and zircon is placed, as you can see, it's not to be doubled each structure, resulting that you can obtain 38 different structures are generated as a calculation model. Here's the result of binding energy in the bare and zircon doped HFSC and HFSC monolayer. Here's the HFSC monolayer's result, and this is the HFSC's result. As you can see, binding energy is all a negative value, means to be endothermic in all cases. Therefore, all bare and doped structure of the HFS3 and HFSC monolayer are stable. Additionally, zircon doping stabilizes structure as zircon concentrations increased, both HFSC and HFSC case. You can see that, you know, the energy dripping as a result. And here's the result of band gap calculation. Indirect band gaps are reviewed both on zircon doped HFSC and HFSC monolayer. This is similar to the bare HFSC and HFSC monolayer. As you can see in the result, you can see the behavior of the band gap is totally different between those two HFS3 and HFSC3 monolayer. In the case of HFS3, you can see that the band gap bowing is seen in the result. Remarkably, HFC band gaps are all above 1.23 electron volts. This 1.23 electron volt means that required potential for the water splitting. So that means that this has a suitable range for water splitting in band gap. On the other hand, HFSC cases in HFSC cases, you can see the band gap formation if the zircon doped. The reason of the band gap formation of HFS SE3 can be explained by the shift of the p orbital of constituent Se atom. Those are the result of the projected density of state of HFSC and zircon doped HFSC monolayer. As you can see, the p orbital of SEC, you can see those green lines shifted to the lower energy. I mean, this is bare form and it shifted to a lower energy going to here. So why band gap is formed? This is the reason band gap is formed by zircon doping. The next discussion is whether doped HFSC is suitable for the water splitting materials. To evaluate this, valence band minimum and the conduction band minimum is evaluated to consider the potential for water splitting. Here is the band alignment of the zircon doped HFSC. As shown in this image, standard reduction and oxidation potential for proton H2 and oxygen water minus 4.44 electron volt and minus 5.60 electron volt. And you can see that all zircon doped HFSC satisfies the evaluated CBM and the VBM potential is good for the suitable for the water splitting. So the zircon doped HFSC can be the candidate for the water splitting materials. And the next study is about the effect of the single atom embedding between the HBN hexagonal boron nitride and two-dimensional black phosphorus heterostructure. This study was reported for the following article with collaboration with the following researchers. In this research, HBN black phosphorus heterostructures firstly designed and evaluated by a first principle calculation. This heterostructure revealed to have 2.25 electron volt of direct band gap. Then single atom is embedded between layers and evaluate the change of electric properties. Here is the image of the embedded HBN black phosphorus heterostructure. Here the embedded single atom is set. The sodium, palladium, platinum, scandium, tin, titanium, silver, aluminum, gold, and iron is selected as embedding single atom in this study. Additionally, the two embedding sites are considered as calculation models. One is the under boron of the HBN monolayer showing this figure. This model is labeled structure A. And another one is under the nitrogen of HBN monolayer showing this image. And this model is labeled structure B. Of course, the ground state optimization is performed in all cases. To discuss the stability of designed heterostructures, the energy between HBN and P layers and embedded single atom is calculated. The values are here. As a result, as you can see, the sodium, palladium, and platinum embedded modules are stable as a heterostructure. So the discussion is focused those on three single atom embedded heterostructures. Next, to consider stability of sodium, palladium, and platinum embedded heterostructure. Projected density of state is obtained. For the PD and the PT cases, you can see that the overlap obtains a low energy level, which indicates to form the covalent bond formation between the embedded atoms and the monolayers. So those two heterostructure reveals to be energetically stable. However, the neutrino cases is something different. To finding the stability of this sodium embedded heterostructure, the charge transfer between embedded atom and the charge transfer is considered between embedded atom and the neighboring atom. The beta charge analysis is performed to evaluate charge transfer. Here's the result, and it shows that in the sodium case, they are positively charged, and on the other hand, the p atom from the phosphorus monolayer is negatively charged. So that means that the ionic bonding is formed because the embedded sodium has a charge transfer to the p atom and phosphorus atom. Additionally, in the case of the structure B, you can see that there's also negatively charged N atom from the HBN layer. That means that structure B forms in a structure B, embedded atom forms the ionic bonding on both HBN layer, monolayer, and phosphorus monolayer. That can be the reason for the structure B is a little bit stable for the structure A. Next is the discussion on the band structure. Here's the band structure, atom embedded heterostructure. And the calculated band gap is estimated in the range of 1.5 and 1.8 electron volt, which is suitable for the optoelectronic devices such as solar cell. As I presented, placed in HBNP heterostructure, the band gap is 2.4 to 5 electron volts. And so that means that the atom embedding is has an effect to lowering the band gaps of this heterostructure. So those research can be classified as what I say brute force methods. Evaluations done in all cases. This method is somehow insufficient for the material design. So yeah, the solution can be provided by materials informatics in various fields. Science and informatics proposed recently. For example, the biology for the bioinformatics, pharmacoinformatics, blah blah blah. And for the material science, it should be material informatics, which is the field to design materials for the material data via data science technique. In the traditional way, materials are designed by experience or inspiration of researchers. This approach is based on try and error, but this is mostly needs a time and a research budget. But however, recently material data is getting easy to collect, and due to the development of analysis instrument and the computer, or simply referencing the accumulated past research data. And so the material informatics is recently paid attention for the effective way to material design. Predicting desirable materials from the accumulated material data via data science technique. Finally, here is the one example research for the two-dimensional design by material informatics approach. And this research is put for the following article with collaboration with the following researchers. In this research, novel magnetic two-dimensional materials is predicted by using the following open computational material database. This database is created by the first principle calculation. And at that time, the data was the 216 data is available. But I think now it's you can available more data, so you can access to check on this website. For the in this database at the time, you can find that MOS2-like and graphene-like two-dimensional material data. So I use those data to apply the data science technique. Yeah, the process is I think it's difficult. I think you guys are not familiar with, so I skipped it. But here is the result of the prediction. By using data science technique, 254 potential candidates are predicted as high magnetic moment two-dimensional materials. I should say that this 254 candidates are not listed in the original 216 data. So this 254 candidates are evaluated by the first principle calculation, and the materials with a higher magnetic moment, enough stability is picked. I mean, the data science can predict something, but they don't consider with the formation energy or some kind of thing. So you need to check by first principle calculation. That's why I did this process. And as you can see, for the enough stability and the high magnetic moment area, you can find that those 8 novel two-dimensional magnet is found in this research. Yeah, that's all. Thank you for your attention.
Thank you, Itsuku Miyazato. Is there any questions for Miyazato? Thank you for your good presentation.
Oh, thank you.
Thank you. Thank you. I have 2 questions for you, but before my questions, I would like to learn if there is another question.
Mm-hmm. Okay.
Is there any questions, dear participants? Okay, there is no question, so I have 2 questions.
Mm-hmm.
You used direct band gap material for your optoelectronic studies. Did you think the usage of indirect band gap material? Did you try it for your research?
Excuse me. Sorry, the voice is
Okay.
I think the
There's the internet problem.
quality of
Okay.
the internet is.
Okay. Slowly, I am asking. Can you hear my voice? Can you hear my
Yes.
voice? Yes. Okay. You use direct band gap material for your study. Did you try indirect band gap materials for your studies?
Yeah, but in this study, I'm focused on the effect of the the manipulation of the structure. So you never know before you calculate. So yeah, that can be indirect band gap materials, but yeah, there's a thing. Do you know what I mean?
Yes, because it's especially chosen for high speed applications. We use the direct band gap materials. Perhaps you choose for this reason. I have second. Okay.
I mean the future studies. If you design the indirect band gap materials, and if you available the how do I say the 2D materials data based from the containing indirect or direct information, you can predict which materials has an indirect band gap and direct band gap by data science technique. Maybe I don't know because I didn't do that. But if data is available, I think I can do that.
It's a bit difficult to excite the electrons when you use the indirect band gap materials. I have second questions. You said that sodium and platinum embedded into your band gap. So, do you think you put embedded sodium and platinum into your material band gap? So, can we think that these materials are taught as a trap center in your structure, and they behave trap centers. This material, trap centers.
Sorry, I don't understand. Trap.
Trap. T-R-A-P. Trap.
Trap.
T-R-A-P. Trap. Trap center. These materials, I think, can behave as a trap centers, or they increase the conductivity according to your presentations. Which one is true?
Trap center.
Trap centers is a state electrons captures from these states, and
it's all stable. I said
stable.
The grand state optimization is performed, so it's all stable.
Stable, unstable, not unstable situations.
It's not unstable, but for the the type of the embedding atoms, some materials are cannot form the heterostructure because of the stability. That's why I said that those trees only those trees are stable.
Okay, those are stable, not unstable, and not trap centers. Okay, thank you. Yeah, I again ask for dear participants, do you have any questions about this presentation? Okay. Dear Itsuki Miyazato, thank you for your contributions for our conference.
Yeah, thank you.
Thank you. Okay, see you.
Yeah, see you.
Okay, the third talk belongs to Yusuf Zuntu Abdullahi. He is from Kaduna State University, Nigeria. He is talk about the electronic and magnetic properties of two-dimensional materials by doping transition metal. Yusuf, Zunt Abdullah, can you hear my voice?
Hello,
Can
can
you
you hear
hear
me
my
now?
voice? Yes, we can hear you, Yusuf. Welcome to our conference.
Okay. Okay, thank you for the opportunity. So I would like to share, I would like to share with you a brief theoretical findings on the electronic properties, magnetic properties of ruthenium dioxide sheet, the distorted octahedral phase based on first principle calculations, and with the hope that the study will provoke further investigations. As we are all aware that with the recent advancement in the quantum technologies, the magnetic nanostructures, and in particular 2D magnetic materials, is currently among the topic of high interest, both for basic and applied research because of their richness in physics and the fact that their properties is completely different from the bulk properties, from the bulk materials. And again, the 2D materials has been synthesized, and many more have been predicted with lots of suitable properties in multiple applications. And among these applications, I think the prominent one is spintronics. And I'm very sure if spin-based electronics is realized, it will ensure the extensions of the famous Morris law, and with spin-based, with spin as a degree of freedom, informations can be processed with very high speeds. So despite the recorded success in synthesizing the 2D magnetic crystals, there is a challenge, and the challenge is the magnetic ordering cannot be withstand at room temperature. So a lot of studies has been done in order to realize 2D magnetic crystals that can withstand the with magnetic ordering, which can be withstand at room temperature. So with the emergence of, I believe with the emergence of the family of transition metal oxide, this challenge can be addressed, because this transition metals comes with a lot of exotic properties, one of which large spin orbit couplings, among others. And this large spin couplings will permit manipulations of spins via external electric field. So this studies actually tries to revisit one of the studies that has been done, which was found to be non-magnetic semiconductor using hybrid functionals by Irshan, and it was published. So we felt that the self-energy has not been addressed. Self-energy has not been addressed, so we decided to revisit these studies using density factor DFT plus U based on quantum, which is implemented in quantum space. As you can see, these are the computational details that has been provided for the calculations. The reason is the octahedral ruthenium dioxide is actually formed by the substitutional doping. And if a substitutional doping over the impurities created would like to arrange themselves in either parallel or antiparallel spin with the spins of the electrons of the ruthenium. And for that reason, the magnetic source has not been addressed with hybrid functionals. So we decided to use DFT plus U using implemented in quantum espresso. And we calculated our own U using linear response approach proposed by Carcacciolo method. And having established the ground state properties, the stability of this structure by the previous studies, the dynamic, thermal, and mechanical stability has been established. So we just proceed directly to determine the actual magnetic ground state. So here we consider 3 antiferromagnetic ground states, and including 1 ferromagnetic and non-magnetic states, as can be seen based on the relative energies in the table provided. The ground state structure of this distorted orthorhombic structure of ruthenium dioxide is antiferromagnetic ground state, and we use the structure to determine the electronic properties. And luckily enough, we found that the gap has been increased, has been enhanced as compared to the one reported previously using hybrid functionals. And it shows indirect band gap with a value in the range of solar spectrum. I think we just saw one paper which shows that the doping the magnetic materials could switch in the antiferromagnetic, as in from antiferromagnetic to non-magnetic state. So we decided to check the effect of charging and discharging. So the effect of charging and discharging here means additions and removal of electrons. So by doing so, and here are the relative energy that we have calculated, and as can be seen, that it is interesting that the antiferromagnetic order switches from a neutral state when there is no addition of electrons, and when the electrons is added into the structures, then it becomes AFM2, and then when one electron is removed from the structures, then it switches to AFM1. So finally, actually, to propose these materials for antiferromagnetic spintronics, it is essential to determine the magnetocrystalline anisotropy, and this is usually is scaled by magnetic anisotropy energy, which is MAE. So based on the calculated values, and as we earlier mentioned, that this type of materials, transition metal oxide, comes with intrinsically large spin orbit coupling. So we found that the value of magnetic anisotropy energy is very large, which is even larger than the value reported for the hexagonal ruthenium dioxide in this form. And then we check the critical temperatures, because the fact that it's antiferromagnetic. So we try to check the nail temperature using within the mean field approximations. And here is what we found. We found value which is slightly above the room temperature. This shows that the ruthenium distorted octahedral phase of ruthenium can be proposed for the antiferromagnetic spintronics. Although this estimated value might be overestimated in the fact that it does not account so many things. So we hope that this has given an idea on how these materials can be used for spintronics. So in short, in general, I think this distorted ruthenium can be used for spintronics. And I would like to acknowledge the support by the Prof. Etam for giving me the opportunity to run these calculations in their own PC. And I'm pleased to thank the organizing committee for allowing me to present these little findings for free. Thank you so much for your opportunity. I think I'm done. I hope you can hear me.
Yes, I can hear. Did you hear? Did you finish your talk?
Yeah, I'm done.
Okay, thank you. So thank you for your presentations. Is there any questions for Yusuf, dear participant? No, there is no questions, dear Yusuf. Thank you for your participation in this conference.
Okay, you're welcome.
Okay. Thank you again. Thank you.
Stop sharing.
Yeah, you can stop.
Okay, is it still sharing? Okay. I stopped. I think it stopped.
But it doesn't work, I think. Why? Sezgin. No, I can't.
Yes, we can continue with the next speaker.
Yeah. Okay, the last speaker is Esra Eroğlu and Sezgin Aydın. Their talks about hydrogen storage properties of semiconductor B4C3. If you're ready, dear Esra, we can start your talk.
Thank you, Hocam. Good day, everyone. Thank you for this great organization. My name is Esra Eroğlu. I'm a PhD researcher at Middle East Technical University. I am doing postdoc with the supervision of Professor Dr. İskender Gökhan and Associated Professor Hande Tufoli. Today, I am going to talk about hydrogen storage properties of semiconducting B4C3 boron carbide layer. In this my study, my collaborator is Associated Professor Sezgin Aydın, Gazi University. Here in my outline, firstly, I am going to begin with introduction and going on with computational methods and then result section. Finally, I will finish my presentation with conclusion part. After the efficient production of graphene, two-dimensional carbon-based nanomaterials have recently become more popular for hydrogen storage studies. Especially, the boron doped graphene and graphene-based systems are promising candidates for hydrogen storage due to preventing the metal clustering, increasing the metal absorption strength, improving the electrochemical performance. In this meanwhile, graphene-based boron compound, boron carbide, it could be a potential hydrogen storage material due to its porous structure, large surface areas, high storage capacities. Furthermore, it has a direct band gap of 2.73 electron volt, with the promise for applications in optical catalysis and optoelectronics, and it has ultra-high sensitivity for gas sensing nano devices. In this study, by using just functional calculations, NH2 hydrogen storage capacity of the calcium-decorated graphene-based boron carbide sheath has been investigated. We use small package program with LDA PDC functional for all calculations, and cut point set is to 441. During the optimization, while two dimensions A and B of the unit cell and all atomic positions are fully reactive, vertical dimension C is kept constant at 15 angstrom to avoid the periodic configuration. All our calculations were performed by high-performance computing center at Gazi University. And let's go on with our results. First, we construct the unit cell of semiconducting boron carbide containing 14 atoms, 8 boron and 6 carbon atoms also, as you can see in figure 1. After the geometry optimization of the unit cell of boron carbide sheet, in order to provide a suitable and sufficient size element for storing hydrogen, 1-to-1 supercell of the boron carbide was constructed and optimized. You can see the optimized geometry of the boron carbide in figure 2. And then to research the hydrogen storage capacity of pure boron carbide layer, we attach from 1 to 10 number of the hydrogen molecule on the layer. Figure 3 shows that the optimized geometry of 4 hydrogen molecules absorbs pure boron carbide system. And in table 1, you can see from 1 to 10 hydrogen absorption energies of the systems for Q and each algorithms. If I have to mention here, I will give you information about these algorithms next time of my presentation. In here, the absorption energies of the systems are found at the range of 0.15 electron volt to 0.21 electron volt. Considering that the appropriate energy range for storing hydrogen is 0.2 electron volt to 2.6 electron volt. These values aren't best at all. After trying studies of pure boron carbide to increase the efficiency of hydrogen storage capacity, we decided to add metal atom on the layer. So we added lithium, magnesium, sodium, and calcium atoms on the system. And we calculated the metal binding energy as you see in the values for lithium, magnesium, and sodium atoms. As a result, we found that the binding energy of calcium metal is lower than the others. So we prefer the calcium metal for our system. Calcium metal is preferred in many hydrogen storage studies due to its advantageous properties. It is known that it has high hydrogen storage capacity of 6 hydrogen molecules per calcium metal. Furthermore, it increases the hydrogen storage capacity by reducing the aggregation tendency. Besides, it's a light metal and it has Cuba's interactions also. After we decided on the type of atom, we tried to find energetically the most tolerable side of calcium metal. So we put the calcium atom on 10 different initial sites, as you see the figure 4, of the layer. As a result, we found 3 different final locations as 8, 3, and 7 for the calcium metal as you see in the table 2. It is found that the hexagon hole, or 8, is the most favorable site with the lowest binding energy for calcium in all sites. So we put calcium metal on the A location for the hydrogen storage studies. And then, to research the hydrogen storage capacity of our systems, we attach from 1 to 10 number of hydrogen molecules on the layer. To increase the absolute number of the hydrogen molecules, the initial coordinates of the hydrogen molecule modeled by Philip and Beach algorithms. To improve the absorption capability and to reduce the computational time, we use 2 algorithms as Philip and Beach. In here, I want to give some information about these algorithms. In Click algorithm, the initial coordinates of hydrogen molecules are generated by using Kepler geometry over the hospital, and which algorithm can be considered as a layered version of Click algorithm. So that first hydrogen layer is designed by using Click, then a second layer is constructed on the first layer by rotating it. The initial from 1 to 10 hydrogen molecules geometries are constructed by using Eclipse. And to absorb more hydrogen molecules per metal atom, the initial geometries of from to 8, 12 hydrogen molecules are constructed by using Eclipse. The optimized hydrogen dot geometries of the system are given in the below. And figure 5 shows us the optimized geometries of n hydrogen molecule absorbed systems, which are constructed by Flink algorithm. As you've seen that after 2 hydrogen molecule attached system, 1 hydrogen bond break off and bonded to the same boron atom. This picture is contained in figure 5. It shows similar properties as the previous geometries. The optimized geometries top and side view of the n hydrogen molecule absorbed calcium decorated boron carbon systems by the which algorithm are given in figure 6. Similarly to the systems of the Philip, the same boron atom broke and 1 hydrogen bound. We calculate structural and electronic properties for all the structures. To investigate the energetic stability and binding nature of calcium decorated boron carbon system, hydrogen absorption energy and band gap energy are calculated, and the results are given in the below. The hydrogen absorption energy and the band gap energy of the n hydrogen molecule absorbed boron carbon system are given in table 3. As you see in the table 3, that the absorption energies are in the range of 0.2 to 0.6 electron volts. By increasing number of the hydrogen molecules, the absorption energy decreases generally. Due to some of hydrogen molecules are located at the surface of the sheet instead of calcium metal. The band gap of the systems are formed as a range of from 1.03 to 2.1 electron volts. So we can say here our system shows semiconductor properties. It's a fact that calcium decorated boron carbon systems are more suitable than pure boron carbon systems for hydrogen storage. Moreover, we analyze the band structure of our system. The band plot of the 6 hydrogen molecule absorbed boron carbon systems by the Curie algorithm is given in figure 7. It can be seen from the plot, our systems shows semiconducting properties, and the band gap for the system is found as 2.1 electron volt. To understand the ionic interactions of the charge transfer of the system, we calculated the electron density differences. The electron density differences top-and side field of the 6 hydrogen molecule adsorbed calcium decorated boron carbon system by the click algorithm is given in figure 8. Herein, the yellow regions represent electron deficiency, I mean the positive charge density, and blue regions represent electron exceed, it means negative charge density, and the ionic interactions and the charge transfers between the hydrogen molecules, the layer and the calcium atom are clearly seen in figure 8 due to the electron deficient region and the electron exceed region. As can be seen from these colored regions, we can say that the calcium atom exhibits an electron donating behavior and the layer exhibits an electron accepting behavior. However, when hydrogen molecules are carefully examined, it's seen that one side of the molecule is yellow and the other side is blue or negative. From this point of view, we can say that hydrogen molecules are polarized. As a result, the designed calcium-decorated graphene-based layered semiconducting boron carbide system could be promising material for hydrogen storage application. Thank you for your listening.
Dear Esra, thank you for your valuable contributions. Do you have any questions for these presentations, dear participants? I think there is no question, Esra. Thank you again. You were my student. I am glad to see you when you're making such a successful talking, and have a great success in your future life. Thank you again.
Thank you, Hocam. Your best wishes. Thank you.
Okay. Dear participants, I want to finish these sessions. We look forward to seeing you at our next scientific events. Thank you for your valuable contributions. And if you have questions, let me know. If you don't have questions, I will finish these sessions. I think there is, okay, I see one question. Okay. Thank you. Thank you for your all participants.
Thanks to the chair.
Yes, yes, Mr. Sezgin.
Thanks a lot.
Thank you.
See you on the next session.
Thank you for your successful organization. I am glad to see such a beautiful conference about, especially about hydrogen energy, because we need to new energy sources in our universe. So thank you again for your successful conference.
Thank you very much.
Thank you. Thank you. Have a good